Well, like to go over some of the problems that we didn't assign in Chapter 6. First problem is Chapter 6, number 7. It's in pages, actually it's on pages 184. They give you this problem. They're asking you to calculate the component currents and the loop voltage for the circuit shown, along with the value of I total and R total. The first thing you want to do is calculate R total. If you notice, R1, R2, and R3 are connected in parallel, and so is R4 and R5. And then the parallel combination of the two sets are connected in series. So those three are connected in parallel, these two are connected in parallel, and then between A and B, they're connected in series. So if I look at the resistance between point A and A, those three are connected in parallel. That gives you 71 ohms, 1 over 1470, 1 over 100, 1 over 510. And the product or the sum for the resistance between point B and B, that gives you 600 ohms. So R total is equal to RAA plus RBB, and that gives you 671 ohms. Then I total would be equal to V of S divided by R total. I got 14 volts over 671. That gives you about 20.9 milliamps. Now, if I look at the voltage at point A and A, that gives you the voltage across those two resistors, because they're asking for the components, currents, and the voltages. So I take I total multiplied by R of AA, that gives you 1.4839. And the same thing with the voltage across BB, that's I total times the resistance R of BB. That gives you about 12.5161. And those three are connected in parallel, so the voltage across R1, R2, and R3 are the same as V sub AA. And the same thing with the voltage across R4 and R5, it will be connected in parallel to be the same as the voltage BB. So once you have the voltage, you can calculate the current. I1 is the voltage divided by 470. I2 is the voltage divided by 100, and I3 is the same voltage divided by 510. If you add those three, this should add up to I total. So 3, 14, 16, 19 should be 20. Yeah. So if you add those three, if you do it right, those three should add up to about 20.9 milliamps. Same thing with the branch between point B and B. You can calculate R5. V sub R4 and R5 is the same, and then you can calculate the current I5 and I4. Next problem is number 10. It says derive the series equivalent circuit for the figure shown in figure 646b. When they talk about derive the series equivalent circuit, you're looking at a point X and Y. So if I look at that, 51 and 39 are connected in series, and that's in parallel with 120. So if I look at the point A to the ground, the resistor would be 51 plus 39 in parallel with 120. If you calculate that, they call that the resistance from A to O to the ground. 90. 51 plus 39 is 90. Multiply by 120, divide by 90 plus 120, that gives you 51.4. Then you put back that in, you got 22 and 33. will be connected in series with a parallel combination we calculated here at 51.143. So that's 55 plus 51.43 gives you 106.43. So that's the equivalent resistance. It would be 106.43 ohms. So that part of the circuit could be replaced. Later on, we're going to look at the technique called Thevenin's, that you can go any points in a circuit. If it's unknown, you make a couple of measurements, you can be able to come out with equivalent circuits. It's like a voltage source connected in series with a resistance, which is a very powerful method in the modeling of a circuit at any given point in a circuit. Excuse me. Next one is problem 15. Please be careful when you do these problems. I know some of you already have problems. Sometimes the figure, it does not really go with the problem right below it. So make sure you refer to the right circuit diagrams when you do the problems. And also the answer in the back of the book, some of them are incorrect. So please take a look at the solution that I do just to verify the answers you might have in the back of the book. Number 15, this is determine the value of load current I of L. So this is the circuit is given right here. We after this current going to the load. To do that, you need to calculate the total current. So 2K, and again, this is a parallel series parallel circuit. So 2K in parallel with 18K. That's just connected in parallel. Then you add that to 330 ohms. But if you notice, you got 10 volts from here to the ground, which is the same voltage from here to the ground, which is the same voltage from this point to the ground. So you can just put that voltage source right here to the ground, so you got plus or minus 10 volts. If you do that, there's no need to combine all the resistance in here. That makes the problem a little bit easier to do, rather than to calculate total current and then use the current divider rule. So giving a problem to see which is the easiest way to minimize the calculation to get to come up with the answer you're looking for. But if I combine these two, then I should be able to calculate the V sub L with a simple voltage divider rule. So 18 in parallel with 2K, that's very close to 2K because this would be a dominant resistance. That's about 1.8K. So if I look at the voltage across the parallel combinations, use the voltage divider rule, V sub L would be equal to 1.8K times 10 volts divided by 1.8 plus 330, that's 0.33K. So V sub L would be 8.45, which is the same voltage that you have here. Even though we find a parallel combination, you still have some voltage from here to here is the voltage across R2, which is the same as the voltage across R of L, and which is the same as the voltage across the parallel combinations. Now we got R of L, which is 2K. We calculate the voltage V sub L. Then you should be able to come out with a current I of L. 8.45 divided by 2K. That gives you 4.225 milliamps. Problem 19, it says determine the V sub L and V sub no load for the circuit shown in figure 649A. So this is the circuit they give you after the voltage across the load as well as the no load voltage. The no load voltage, that means remove or open circuit the load. So if I remove the load, then you got 8 volts in parallel across the series combination of R1 and R2, so you can simply do a voltage divider rule. So V no load would be equal to 8 volts times R2 divided by R1 plus R2, simple voltage divider. So it'll be 8 times 30 divided by 30 plus 10. That gives you 6 volts. So ideally, you're really having a voltage divider supply here. You got 8 volts. You should be able to get 6 volts out of this combination here. Now, when you put a load in, again, the rule of thumb is at least there should be 10 times this or 30 times that in order to get good voltage regulation. But this is very small load, resistance of the load, therefore you're going to load down the circuit. Now if I look at the parallel combination for the calculated voltage V sub L, that brings us down to 24 ohms as opposed to 30 ohms that we had initially at no load. And then if you do a voltage divider there now, it's 5.647. Problem 23, it says determine the normal range of the output voltage for the circuit shown in figure 651A. Again, you got a voltage divider supply here. You have a load. The load range V sub L is equal to 5 volts, but the current, it could go anywhere from 20 to 50 milliamps by adjusting the resistance value of the load. So if you calculate R of the load, the range of R of the load would be equal to VLO times R of the load. So the minimum value for the load would be equal to R of the load when I of L is maximum. So plug in 50 milliamps, that will give you the minimum value for R of L. When I of L is minimum, then you have the maximum resistance of the load. So that gives you the two limits. So the R of L would go from 100 ohms to 250 to give you 20 to 50 milliamps current. So at one extreme, when it's 100, then you just got to do simple calculation. Again, you're going to find a parallel combination of those two, and then V sub L would be equal to 10 volts times the parallel combination here, which is 10 in parallel 100, divided by 10 in parallel with 100 plus 9.1 volt, 1 ohms. And if you carry that, carried out the calculation, it gives you 4.99 volts. The other extreme, maximum load, 250 ohms. Then you got 10 will be in parallel with 250, so you'll repeat the same calculation, replace 100 with a 250. Parallel plus 9.1, and that gives you 5.14. So therefore the load would vary from 4.99 to 5.14, depends on the resistance of the load. Problem 29. It says perform Y to delta conversion for the circuit shown in figure 654. C. And I'm assuming 654C, they're referring to the third diagram in there, which is a Y connection. And so you want to do Y to delta transformations. So this is the circuit that is given here. It's a Y connected R1, R2, and R3. And you're going to put on there your delta. Here. That gives you a delta. Now the way you remember this, if you want to calculate, the way you number the resistance R of A is directly across from point A. The resistance R of B will be across from the angle B, and R sub C is directly across from point C. The way it works out, if you don't want to memorize the equations, if I look at R of A, which is this resistance right here, would be equal to, the numerator would be the same, would be sum of the product of the two resistances at the time. So it'd be R1, R2, R1, R3, R2, and R3 for all three of them. But for R sub A, R sub A is directly from A, so that has hooked up to a resistance R1, so we divide by R1. For R sub B, that's directly from point B, and R2 is connected to point B. And then RC will be R3. So you already have equations. You plug the values in, calculate the resistance R1, RB, and RC. All right. Next problem was number 37. It says for the circuit shown in figure 655, determine the adjusted value of R2 that will cause the load 1 to run at its rated value. Everything is given. You have an adjustable resistance here. It's a 1K ohm. It could be a potentiometer with a point B and C or A and C connected. You want to vary that such that the load 1 to run at its rated value. Rated value is equal to 2 volts, and I of L is equal to 1 milliamp. Now, to determine the resistance R2, we must calculate how much current is going to go through that. Call that a current I2. And we also need to know the value of the voltage VAB, which is the value of the voltage across the resistance R2, which is equal to V sub A minus V sub B. So I need to calculate the voltage at this point, and as well as the voltage at this point to the ground, and then subtract it to give you the voltage across the resistor. And then if you calculate the current I2, then you should be able to calculate the resistance value. Now if I look at V sub A, which is this voltage from this point to the ground, which is the same voltage across R5 and the load 2 to the ground. But we know how much current is going here. It's 4 milliamps. So I can calculate the voltage VA. It's R5 times 4 milliamps plus the voltage across the resistors, the load number 2. So V sub A would be equal to V sub L2 plus R5 times I L of 2. 8 volts for V sub L2, 750 times 4 milliamps rated current. That gives you 11 volts. Same thing with V sub B. V sub B would be equal to I of L times R4 plus the voltage VL1, which is 2 volts. So I give you R4 times 1 milliamps. I4 is 1K. 1 milliamps is equal to 3. Therefore, V sub AB, which is equal to voltage across the resistance R2 that we're looking for, is 11 minus 3 is 8 volts. Now, to calculate the current I2, current I2 would be equal to whatever the current, we call that current IL2, okay, minus the total current, or if I calculate the current I2, if I know what the current I3 is, then I2 would be equal to I3 plus I1, IL1. There are two ways you can calculate, but it's easier to calculate because we know how much voltage we have here, and we can calculate the current I3, and we also have the current I of L1, then it makes it a little bit easier. So I2 is equal to IL1, that's 1 milliamps. I3 is V sub B divided by 300 ohms. That gives you 1 milliamps, and 0.01 gives you amp, which is 10 milliamps, so that gives you 11 milliamps. Therefore, R2 is equal to V sub AB, which we calculate to be 8 volts, and I2 is 1 plus 10 is 11 milliamps. That gives you 727 ohms. That should be page 189. Problem 38 is to determine the value of V sub 6 for the circuit shown in figure 656. And V sub 6 is a voltage across the resistance R6. Excuse me. I can combine those two values, 240 and 360. It gives you 144. So I can replace those two with 144 ohms. 144 plus 150, that gives you 294. I'm going to call that point A here, that's point B. So the circuit will simplify to this. 330 would be in parallel with 294, and then 150 to the ground, and then 120 to the ground, and 100. So the circuit will simplify. If I look at RA to the ground, at the terminal right here, to the ground, those two are connected in parallel, plus 150, and all of that is in parallel with 120. So I need to calculate a parallel combination here, add it to 150, that's connected in series, and then the result of these three be connected in parallel with 120. So 330 in parallel with 294, it gives you 155.48. Add that to 150. Right here. Add that to 150. We'll look in the circuit 3. 155.48 in parallel with 120. So the resistance from here to the ground is equal to 86.15. So if I use a voltage divider rule, I can calculate how much voltage I have from A to the ground as 6 volt times 86.15 divided by 100 plus 86.15. That gives you 2.776 volts. So I go back to the circuit. If I look at the circuit 3, which is the circuit right here, we know how much voltage we have, V sub or AO. So I can calculate the voltage at a point B. So V sub A to B then, which is this voltage from A to B, would be equal to the total voltage, which you calculated. That's the voltage across 155.48 ohms. Would be V sub A 0, which is 2.766 that we calculate. It's a simple voltage divider. So that gives you 1.4133. That's the voltage from point A to B. So from A to B is equal to 1.4133. And the voltage V sub 6 that we're looking for is the voltage across those 360 ohms. And we already calculate that. The parallel combination of those two is back up here. That was R5 and R6. That was 144 ohms. So voltage A to the ground is equal to the voltage across 150. The voltage from A to B is the voltage across 150 in a parallel combination here. So V sub 6, all I have to do is go back here and calculate the voltage that is dropped from point A to B, the portion of the voltage that will drop across the parallel combination here, which is 144. So if I do voltage divider rule, V sub 6 then would be equal to the total voltage times the parallel combination here, which is 144, divided by 144 plus 150. And that gives you a 0.6922 volts. So you really want to look at the circuit 3. Once you calculate V sub A to the ground, then you can calculate using a voltage divider rule to calculate the voltage from A to B using a voltage divider rule. once you have the voltage A to B, you go back here, you got to do the voltage divider rule again to calculate the portion of the voltage that it drops across the parallel combination here, which is 1 across 144 ohms. That's one way to do the problem. The other way you could have done it is to calculate the total current and then use a current divider rule to see how much current is going to flow through the parallel combination here, and then you can use the current divider rule again to calculate how much current the total coming in is going to split up between those two. So either with the voltage divider rule or the current divider rule. But I think it's a little bit easier if you're going to use the voltage divider rule, because you get to apply it twice to come up with the voltage that you're looking for. The last problem, which is problem 41, they give you the alarm triggering circuit shown in figure 659 has the following characteristics. One, it activates the alarm when the voltage at the input Y. So your alarm activating circuit, it has two inputs. One is a point Y and the input X. When the voltage at input Y is the same as is equal to the voltage at a point X, then the alarm will get activated. The voltage at a point Y is provided by the digital thermometer, and the output voltage of 0.05 volts per degree Celsius. So this acts like a transducer, whatever the temperature is. Take that temperature, put an output voltage here, putting out a voltage at 0.05 times whatever degree Celsius is. So for every degree Celsius, the output will be 0.05 volts. V of X is a reference. The voltage at X is a reference voltage that is determined by the setting of the R2, which is a potentiometer, 10K ohm potentiometer. So this is your reference, your set value. Let's say you want to set it at, this thing is calibrated in terms of the temperature, and so you want the alarm to go off, let's say at 200 degrees Celsius. Then you put this on 200 degrees, and then when the output of your digital thermometers reach that reference voltage, then we'll trigger the alarm and the alarm will go off. But the problem, but it says that the X and Y inputs each have a value of the input impedance, input resistance of 10 mega ohms. That is, each appears at a 10 mega ohm load to its input circuit. The reason you want to do that, from problems that we looked at so far, if this circuit right here does not have high input impedance, in other words, it doesn't have very high resistance as a load, then you will have a loading effect. You've already noticed that every time you put a small resistor connected in parallel with your voltage divider, or your potentiometer as a voltage divider, then that has tendency to lower the voltage, and it creates inaccuracy in your system. You're loading down the circuit. To avoid that, there's ways you can do that. Probably maybe later on in the semester we might get into this. It's called high input impedance. You can use certainly operation amplifiers as a high input impedance. When you do that, you're really minimizing a loading effect, such that when you hook up the circuit, this voltage reference is not going to change, which is something that you like to have. That's already been done. So the alarm triggering circuit, you had a high input impedance, and it's not too difficult to do that with operation amplifiers. Now, it says what adjustable potentiometer value, that is the value of R of BC, That should be a point B here to the ground, where you want to set it such that the alarm will go off at 120 degrees Celsius. So when the temperature reaches 120, it could be a process control, whatever the case might be, that the alarm will go off. So at 120 degrees Celsius, then the voltage at the Y terminals, the Y input, would be 0.05 times 120 times 120 degrees Celsius. Celsius to Celsius will cancel out. 120 multiplied by 0.05, that gives you 6 volts. So this thing has been set such that it's calibrated 120 degrees Celsius, and then when the temperature reaches 120, then you have the same input voltage, and then the alarm will go off. So if I look at that circuit, you want to have from point B to C, you want to have 6 volts, and again, this is a high input impedance, so you don't have to worry about the loading effect. So you'd like to have 6 volts to be 12 volts times R of BC plus R of BC plus R of AB plus 1K. But R of BC plus R of AB, that's your total potentiometer setting, which is 10K. So it'll be 6 is equal to 12. R of BC that we're looking for. Those two will give you 10K plus 1K, it gives you 11K. So R of BC then would be equal to 6 times 11K divided by 12. And that gives you the value of R of BC to be equal to 5.5K. So all you have to do is set the potentiometer here at 5.5K. Then the alarm will go off. You calibrate the alarm to go off at 120 degrees Celsius. And you can draw it the same way. This is 12 volts, R1, then R of BC, where R1 is equal to 1K plus R of AB. It's just a simple voltage divider. You can set it up. All right, those are all the problems that we had in Chapter 6. Please take a look at them. And if you have any questions, just send me an email. We'll be happy to discuss them. We'll stop here. Thank you.